By the way, a little aside, the derivative of the natural log of the absolute value of u is actually, the definition is exactly the same. And there's a little bit of a mini proof to that. Remember, when we have absolute value, I always suggest rewriting things as a piecewise function. So the first thing we're going to do is we're going to let y equal the natural log of the absolute value of u. The next step is then to write it as a piecewise function. So that's what I wrote here. And then you're going to take the derivative with respect to x of each of the pieces. So that's how to deal with a piecewise function. So step number 2, I'm just taking y prime, taking the derivative of, oh, I did not mean to erase that. Whoops. I'm just taking the derivative of the natural log of u, which is 1 over u times u prime. Then if I'm taking the natural log of negative u, it's going to be 1 over negative u, but taking the derivative of that gives me a negative u prime, and that means that when I multiply these two together here, 1 over negative u times negative, the two negatives cancel out. So regardless, once we simplify, both of them are still going to give me u prime over u, no matter whether it's positive or negative. Okay. Let's try some of these. There's multiple ways you could do this. One way is to, and I'm going to have you try this one. At the beginning of this, remember I asked you to rewrite 2 to the x as e to the natural log of 2 times x. That is the same thing. And don't forget, the natural log of 2 is an actual value, like a decimal. So if I'm taking y prime, remember, the derivative of e to any power is itself, so e to the natural log of 2 times x, times the derivative of the exponent. But look, the natural log of 2 is just some coefficient of x. Like if I had d dx of 2x, it would just be 2. If I have d dx of 3.175x, the answer would be 3.175. Well, the same here. Now, it's the natural log of 2 is just some decimal. So when I take the derivative of the exponent, it's going to be the natural log of 2. So that means then when I'm taking the derivative, it becomes e to the natural log of 2 of x, but e to the natural log of 2 is actually equal to 2. So I can now go back and replace this and write 2 to the x times the natural log of 2. Now there's an alternate way of showing the same thing. You could rewrite this in logarithmic form. So I could say, okay, well, I'm going to rewrite this as, or now I'm changing my mind, like take the natural log of both sides would probably be the easiest. I could do 2 natural log of 2 to the x, then bring the x out in front. So then we get the natural log of y is equal to x times the natural log of 2. And then you can take the derivative of both sides. So dx of the natural log of y is equal to dx of x times the natural log of 2. So in this case, on the left, we get 1 over y dy dx is equal to, and on the right, it's just going to be the natural log of 2. So then, oh, I'm running out of room here. This is going to give me dy dx is equal to y times, I'm multiplying both sides by y, the natural log of 2. But y is defined as, up here at the start, we defined y as 2 to the x. So it's going to be 2 to the x times the natural log of 2. So that's 2 ways of showing what the derivative becomes. So I want you to pick one of the 2 ways to find the derivative of y of 3 to the x, and then try to generalize for any value here. So whichever method you prefer. Hit pause, and you should write out the work for those. you should be getting y prime is equal to 3x times the natural log of 3. And this one, I'm hoping you got y prime is equal to a to the x times the natural log of a. And that is the actual derivative of any exponential function where the base is not e. You just have to multiply by the natural log of a. And keep in mind that you do the same thing using the chain rule. I'm going to give you some advice. These tend to be easier if you think of them in words. So I would write, this is always itself times natural log of base times derivative of exponent. So it's like a little rhythm that you get into. So if you look at the first example, I have an exponential function. All right, finding the derivative, f prime of x, the answer is it's itself, 5 to the 2x, times the natural log of the base, natural log of 5, times the derivative of the base, times 2. So I'm going to put that in parentheses and then pull the 2 out in front. 5 to the 2x times the natural log of 5. Same for b. Try b right now. So like say it in words to yourself. dy dx is equal to, first of all, it's just this part that's raised to the exponent. So it's going to be 3 times and then take the derivative. That's a constant multiplier. So it's 3 times itself, 2x minus 5, times the natural log of the base, times the derivative of the exponent. So dy dx in this case is equal to 6 natural log of pi times, oh, I was going to write e. I meant pi. Pi raised to the 2x minus 5. For part C, all right, we got to use the base here, same idea. The base just happens to be the natural log of 2, which is some number. So same thing, itself, that's the natural log of 2 raised to the 3x times the natural log of the base, which is the natural log of 2, times the derivative of the exponent. So that's 3. So 3 times the natural log of 2 times the natural log of 2 raised to the 3x. Now try D. Pause it and try D on your own. It just has 2 parts. That's it. That's what I'm getting for those.